Hello everyone. In this video, we are going to discuss in detail about the Hall effect. And in this video, I will be explaining you that how we can use a virtual lab to perform the experiment of Hall effect to find out various electrical properties. The aim here of our experiment is to determine the Hall voltage developed across the material and to calculate the Hall coefficient and the carrier concentration of the sample material. For this, we required the apparatus, we required solenoid, then constant current supply, a 4 probe, then digital Gauss meter, a Hall effect apparatus which consists of constant current generator, digital multimeter or voltmeter and Hall probe. So these are the apparatus which we required. But before performing and directly going to see how we can do this Hall effect experiment virtually, let's see the basic theory related with this Hall effect. So what is Hall effect? Hall effect that was discovered by Edwin Hall in 1879. And what is it? Here you may see in this image sample material, a semiconductor sample material, which has certain thickness T, it may have certain width D, and you may have its length that is L. And this sample material to which we applied a magnetic field. You can see these blue lines. This is the way or this is the direction in which the magnetic field is applied to it. And normal to this magnetic field, we are passing an electric current through this sample. Then it is observed by Hall that when we have such kind of arrangement, then on remaining two sides, that is this back side and this front side, across these two sides, a voltage that is generated, which is known as Hall voltage. So here you see, if a metal or semiconductor carrying a current I, as shown here, is placed in a transverse, that means perpendicular magnetic field, a potential difference produced in direction normal to both magnetic field and that of current. So here you see the magnetic field is vertical, we have upward, the current that is passing through this particular sample in this direction, then perpendicular to this current and magnetic field that is on this side. So across those two sides, a potential difference is generated, which is known as Hall voltage. And this overall effect is known as Hall effect. Now once again, we will see how it happens. Okay. So the same sample that I am shown over here. And suppose that we are passing an electric current, okay, in this x direction. Let me call this particular direction as a x direction. So if I am passing this electric current in x direction, that is along this direction, and suppose if I apply a magnetic field, if I apply a magnetic field which has the field direction, let's suppose that is we have horizontal like this. Let me call this particular direction as y direction. So this is the magnetic field which we are applied normal to the current which is passing through this substance. So now which two surfaces of this sample are remain, that is this top surface and this bottom one. As per Hall effect, okay, we know that if you connect these two surfaces to a voltmeter, if I connect here this to a voltmeter, then this voltmeter will show me some voltage. So how the potential difference that is generated across these two surfaces? Let's see, when a charged particle, okay, let's suppose these are charged particle which are, okay, traveling or which are passing through this particular sample with velocity v, then as this charged particle, let's say q or e, when it is passed with velocity v through this particular material, in this way, then as this magnetic field is perpendicular to the velocity vector of this charged particle, then definitely on this charged particle a magnetic force will act. Do you know what is that magnetic force which is acting on this charged particle which is moving with velocity v through a transverse magnetic field? Yes, it is given by, so this magnetic force which is acting on that charged particle, we can get it by E in bracket V cross B. V cross B. Or its magnitude we can write as EVB sine theta. Now here as the V and B they are normal to each other, so we can write this magnetic force which is acting on it, that would be EVB. So this much magnetic force that acts on that charged particle. Now in which direction this force act on that charged particle? Do you know how we can find that? So here we can find that direction of force by using Fleming's left hand rule. Fleming's left hand rule. What it says, what this rule is there? If you stretch the thumb, the forefinger and the middle finger so that they are perpendicular to each other, then here this thumb indicate the direction of force, this forefinger direct towards the magnetic field, and this middle finger indicate the direction of current. So here if you think and apply Fleming's left hand rule over to this charged particle, see, so in which direction the force will act on this charged particle? As we apply magnetic field in this, okay, so just stretch the fingers of your left hand, the forefinger in the direction of magnetic field, show the direction of the middle finger that indicates the direction of current, then you see your thumb will point upward. It means this magnetic force will act on this charge. So those who are traveling through this transverse magnetic field, they will observe a magnetic force and they will be get raised to this top surface. So these charged particles start accumulating at this top surface, and slowly this number of charges which are accumulating on this surface that increases. And as here, suppose if this is positive charge, if they get accumulate over here at this top surface, then by induction a negative potential will be developed across the other or opposite surface. It means here a potential difference across these two surfaces that is get developed or generated, and this is nothing but Hall effect. Now, till when these particular charges are accumulated on the surface, you see, as here this particular positive charge are get accumulated, and electric field that is generated in this material, and its direction from positive to negative we have. So as this electrical field is get developed and it goes on increasing with the accumulation of this charge on this top surface. So because of this electric field now, an electric force that will be get developed, or electric force that will be also get exerted on this charged particle, and this electric force that would be here in downward direction, in the direction of this electric field we have. Do you know how much that electric force? It is E charge into electric intensity E. This is electric force. Now if this electric force which is acting on this charged particle moving through that particular substance, if it becomes same as that of this magnetic force, which is taking that charged particle at top surface, if those become equal to each other, and at a certain time this electric force it becomes same as that of this magnetic force, and once they become equal but opposite to each other, then this charged particle they stop moving to those surfaces, and then after that they will just go directly through this particular substance without any deflection. Where equilibrium is reached, if I put their values, then let's see what we get. So electric force is E into capital E, that is equal to magnetic force is EVB. So on both sides this electric charge E, if I cancel this velocity V, I could get here that is E upon B. And this velocity is nothing but the drift velocity. Now we know the relation between current density J and the carrier concentration N, the charge and the drift velocity. So current density is given by NEVD. If I put the value of Vd from this equation over here, I will get J is equal to Ne into capital E upon B. Again you see this electric field also we can find by the relation, that is potential difference across these two surfaces divided by distance between them. So if I consider this distance as d, this distance as d, this thickness of material, let's say it is we have T, then here this electric field, for this electric field E, I can write the electric potential, which we can say here as a Hall potential or Hall voltage divided by D. And this value if I put over here, then I'll get J is equal to Ne. For E I can put VH upon this B and that D. So by this equation I can write VH, the Hall potential, in this case that is equal to J B D upon N into E. Or for current density, okay, generally we know the current passing through the sample. So current density we know it is I upon A. If I put that value here, I can write it is IBD upon NE into A. Now A is what we have. A is this area. And this for area, I can write D into T. Okay. So if I put that value, so again I can simplify further. So IBD upon NE into D into T. So this DD would get cancelled. So finally, I'll get here this Hall voltage. Let me write here this Hall voltage here, that is equal to IB upon NE into T. So this is the Hall voltage for current I. So for a fixed value of B and for a particular thickness of material and this N and E, these constants, so this Hall voltage you see is directly proportional to the current which we are passing through that sample. Here once again the Hall coefficient we define as 1 upon Ne. So if I put here for 1 upon NERH, then I can also write this Hall voltage is equal to RH IB upon T. Or one may write this RH is equal to VHT upon IB. So I hope you understood how we can find this Hall voltage or how Hall voltage that is produced across those two surfaces and their relation. And by using this relation only, one can find this carrier concentration, the Hall coefficient, the Hall voltage, etc. As well as one can find the mobility, let me write here, mobility of charge carriers is represented by mu, which means how much drift velocity those charge carriers have in a particular electric field. So it is Vd by E. Now by this current density relation, okay, for this Vd, if I write it is equal to J upon Ne, so I can write it is J upon Ne into E, which is mobility. And again, this J by Ohm's law, which means we have the conductivity into electric field. So divided by this, I can write as Ne into E. So this both E will be get cancelled. So this mobility is equal to I get conductivity upon Ne. And 1 upon Ne means Hall coefficient RH into sigma. So the mobility of charge carrier also we can find by performing this experiment. So like this we can find various properties related to charge carrier by performing this experiment. So this is very important experiment we have. Now we will see how we can perform this experiment virtually. Okay, so here is the page which I opened of Amrita Vishwavidyapitam. Now let's see here. This is the experimental setup for Hall effect experiment. These two are the two solenoids which are connected to a source of current. Here we have one wooden plank. Then this particular probe is a Gauss probe we have, which is used to measure the magnetic field produced in between these two solenoid. Okay, and to read that we have here Gauss meter. So very firstly what we have to do, that you can see on the right side there are variables. So on select procedure, below the select procedure, you find there are two options. One is magnetic field versus current and Hall effect setup. So first of all, we'll do the first part, that is magnetic field versus current setup. For this, we need to insert a probe. So if I click that, the probe will shift to this wooden plank. Then if I just click on this wooden plank, then this probe will actually we can place it in between this solenoid. Okay, and the current which we are passing through this solenoid right now it is 1 ampere, and for this 1 ampere current you can just note down this magnetic field produced between this solenoid, which is 0.1482 Tesla. Now to note down this reading you can make an observation table. Let me show you. So here for the first part you have to make an observation table for magnetic field versus current setup. Make 3 columns. Here you can take number of readings. Better you take here 6 readings. Then current through a solenoid that we can change. How we can change I will show you, and for those current you need to note down the magnetic field generated. So here you see for 1 ampere current, whatever magnetic field you get, you can write down in that observation table. Now let me increase this current by pressing this arrow. Now you see how much current I make? 1.5 ampere. Note down this magnetic field. Let me change it now. Yes. So you just note down the current and its corresponding magnetic field which is produced in this solenoid. This is your fourth reading. Note down the fifth reading. This is your reading number 6. And let's take one more. Yes, this is your last reading. So here the first part of this experiment is over. Now I will remove the probe, and now I will select the Hall effect setup. You see as I press Hall effect setup, instead of gauge meter, now I have a Hall probe where you can see there are four wires which are connected to these four ends. And in between these four, there we have a very small thin piece of a sample material. Okay, then here I inserted the probe, and then if I click on this plank, the material that we are placed in a magnetic field. So these four wires, out of that you may see two wires, those are connected to a current source. It means current is passing through that particular sample in a particular direction, and we are place it in a normal magnetic field, and the remaining two wires, those are connected to a voltmeter. So here we can check how much current that is we are passing. You see it is in milliampere. Right now 1 milliampere current that we are passed through this probe, and that we are placing this magnetic field. Now we can select here material as well. So let's select a material. Here there is a list of material we have. This is a semiconductor material, and below to that we have metals. So let me just take here germanium. The thickness of this sample is provided to us, which we need in calculating Hall voltage, etc. Then the Hall current, that means current that we are passing through that probe. Just now we have it is 1 milliampere. Now in this case, how much voltage is generated? Let's see. So you can see here, now this red button switched to millivolt, and you can just see on this display how much voltage that is developed. So this is your Hall voltage. This is your Hall voltage. So to note down these readings, you have to make an observation table like this, in which for Hall effect setup, first of all, you have to keep the magnetic field constant by passing current constant through a solenoid. You need to write down that. From this above table, you can note down those values. Thickness of sample, that is also displayed. Now you have to make three columns where you just go on writing this Hall current, which is in milliampere, and for that you just find how much is Hall voltage, and using these values and formula you can find the Hall coefficient. Yes, so for 1 milliampere Hall current we have this is Hall voltage. Now let me change it, and you can just write down the values of Hall current and Hall voltage. So this is current we have milliampere, and C, this is the Hall voltage. This is Hall current, for which you can get this is Hall voltage, the third reading. This is reading number 4. Observation 5. This is 6th. We will take one more. Okay, so I hope that all of you are written those observations. Now, once you filled this table with the observations, you can calculate Hall coefficient by a formula which I was already explained to you. What is that? Let me once again write over here. So RH we can find by calculation as RH is equal to VH, the Hall voltage, into thickness divided by current into magnetic field. So Hall voltage here already we have. Thickness that you must be taken here, note down here. I, that is Hall current, and B is this constant magnetic field. Put these values and find this Hall coefficient and see their values are exactly same. Now this value of Hall coefficient we can also find by graph. So how we can do that? So for this purpose, you have to plot a graph of Hall current versus Hall voltage. What I mean by that, on y-axis you plot the current and on x-axis you take the value of voltage and just plot the points and connect it. So as there is a direct proportion, you may get a straight line. Then find the slope of this graph. That is, any 2 points of this straight line you connect as shown here. So this particular length over here is a delta y, which gives you current, and this horizontal distance, that is delta x, which gives you Hall voltage. So this is the slope of this graph. So slope of this graph will give you the current and voltage I by V. Now once we get this slope, write down the value of slope over here of the graph. Whatever you obtain that slope, you just write down that here. Now from this slope we can find the value of carrier concentration, that is N. We know that Hall voltage VH is equal to, we have IB upon NE into T. Now from this relation we can have this carrier concentration N, that is equal to IB upon VHET. Now here this I upon VH gives me the slope. You see, I upon VH, it is nothing but the slope that we find from the graph. So to this slope, if I multiply by magnetic field and if I divide by the charge into thickness, I will get the carrier concentration. This Hall effect experiment has a lot of importance. We can find the different types of semiconductor. It means whether a semiconductor is P type or N type, which we can find by finding the sign of majority charge carriers. Also, we can find the carrier concentration as just we are seeing in a lab. Then also we can find mobility of the charge carriers and drift velocity of these majority charge carriers. So these various electrical properties we can find by doing this Hall effect experiment. Thank you.